Welcome to the training module 18 on testing and commissioning of electrical grids. Today, we'll focus on the crucial processes of final trip settings, normalization, and energization. This module is designed to provide you with a comprehensive understanding of how to safely and effectively bring an electrical grid into operation. Let's dive in and explore these key steps together. Here we have the reference framework for testing and commissioning electrical grids. This slide lists key standards organizations like the IEC, IEEE, ASTM, NEMA, ANSI, SIGER, ICA, and KEMA. Each plays a vital role in defining protocols and best practices. It's important to note that when project specs, manufacturer instructions, and standards differ, we apply the most stringent approved requirement. Also, documenting which reference standard was used during testing is critical for future traceability and review. This ensures consistency and reliability across all commissioning activities. Here we focus on the testing and commissioning of the electrical grid, specifically the final trip test, which is a crucial step to ensure system reliability and safety. This test is thoroughly detailed in Commissioning Manual Number 18, which acts as a reference for instructors during explanations, field walkdowns, and evidence reviews. Key components involved include current transformers, voltage transformers, and the substation automation system. Understanding the sequence of events during the test helps us verify that protection systems respond correctly under fault conditions, ensuring the electrical grid performs as intended under all circumstances. Here we have the final trip test procedure for testing and commissioning the electrical grid. The main goal is to confirm that every approved protection element trips through the complete final trip path, starting from the main 1 and main 2 relay outputs, through the lockout and trip circuit relays, and finally to the circuit breaker operation. We reference important documents like the WING 6460-002-093, the approved protection settings, final setting packages, and single-line diagrams to ensure everything is aligned. Next, the instruments used include the secondary injection test set, relay output interfaces, test kits, multimeters, and proper PPE to maintain safety. The testing follows a step-by-step script. First, a thorough visual inspection and verification of permits and lockout-tagout boundaries. Then, relay settings are reviewed before starting any trip simulations. We carefully connect test equipment without bypassing any safety controls. The main 1 relay trip elements are simulated one by one, including protection functions like 5050N, 87L, 2759, and others. Each operation is verified through lockout relays, trip circuit relays, and the circuit breaker trip coil, recording breaker open indications, alarms, event logs, and loop timing. The process is then repeated for main 2 relays, and finally, all test switches and controls are restored to normal approved conditions. Acceptance criteria are critical. Every trip element must operate correctly, the breaker trips reliably, loop times are recorded, and no false or missing trips occur. All evidence must match the test actions. Documentation and evidence include the test sheets, relay reports, timing records, breaker confirmations, event logs, SCADA screenshots, and witness signatures. A hold point requires approval from commissioning authorities, protection engineers, and operators before breaker trip simulations start and before restoration. This ensures a thorough, safe, and documented final trip test for electrical grid protection commissioning. On this slide, we focus on the critical process of testing and commissioning the electrical grid, specifically related to relay final settings for extra high voltage, medium voltage, and static VAR compensators. It's essential to meticulously review these settings to ensure the protection and reliability of the entire system. The Commissioning Manual Number 19 serves as our key reference throughout this process, providing detailed guidance for instructors during explanations, field walkdowns, and evidence reviews. Keep in mind the important acronyms here. PD stands for Protection Engineering Department, CT and VT are current and voltage transformers respectively, and SOE and SAS refer to sequence of events and substation automation system, each playing a vital role in the overall commissioning workflow. This slide covers the critical process of reviewing relay final settings for EHV, HV, MV, and SVC protection before energization. The key objective is to ensure that all relay settings are accurately downloaded, printed, and thoroughly compared against approved configurations, CT and VT ratios, and marked up drawings. First, settings are downloaded directly from each relay under supervision and printed. Then, native setting files are saved in a secure location as electronic evidence. We compare these printed settings with the approved final settings to identify any discrepancies. Every check setting is highlighted, and any issues are resolved promptly. Only approved modifications are marked using a red pen, with discrepancies escalated to the team leader or senior commissioning engineer for approval. The final settings checklist must be completed, signed, and all documents organized in indexed folders for scanning and archiving. Energization cannot proceed until this comprehensive review package is complete, signed, and all discrepancies formally closed. The acceptance criteria demand agreement across all documents, ratios, and checklist, ensuring a reliable, evidence-backed protection system ready for operation. On this slide, we're focusing on testing and commissioning electrical grid, specifically the process of normalization before energization. This step is crucial to ensure that all systems are properly configured and safe before we apply power. The commissioning manual referenced here, Manual Number 20, serves as a comprehensive guide for instructors to lead detailed explanations, conduct field walkdowns, and review evidence to confirm readiness. Key terms like CT, VT, SOE, and SAS represent important components and systems involved in this phase, ensuring thorough protection and automation checks. Understanding these elements helps us guarantee a smooth and secure energization process. Now, let's focus on the normalization process before energization, which is a critical step to ensure everything is properly prepared and safe. First, we need to verify that all CT and VT circuits are normalized. This means confirming correct connections, ensuring any required shorting or isolation is in place, verifying single-point earthing and tight terminations, all in line with marked-up drawings. Next, for transformers, reactors, and outdoor equipment, we remove temporary grounds or shorts, close covers securely, check for no oil leaks, and confirm settings like NER grounding and OLTC tap positions are correct. Power cables must be thoroughly inspected, including terminations, sheath connections, link boxes, and fire-stopping measures. Trip circuits and alarms require normalization too, ensuring selector switches, links, and alarm statuses match the approved final settings without any standing alarms. Auxiliary systems, including ACDB, DCDB, and auxiliary transformers, must also be checked for proper cable and fuse conditions without any temporary grounding or leaks. The acceptance criteria are that all circuits and equipment are in the approved as left state with no temporary grounds, shorts, or defects remaining. Documentation is equally important, so we compile the normalization checklist, sign-offs on marked-up drawings, proof of CT/VT circuits, photographs, alarm screenshots, walk-down records, and witness signatures. Finally, before energization, there is a hold point where operations and switching authorities must accept the normalization checklist to release the energization permit. This ensures a thorough, systematic approach to safe and compliant commissioning. Here we focus on the critical phase of testing and commissioning the electrical grid. This process ensures that every component is functioning correctly before full energization. The commissioning manual, specifically Manual Number 21, provides detailed guidance used during instructor-led explanations, field walkdowns, and evidence reviews. Key terms to understand include CT for current transformer, VT for voltage transformer, and SAS for substation automation system. All essential elements in ensuring a reliable and safe electrical grid. Following these procedures meticulously is vital to prevent issues once the system is live. On this final slide, we focus on the critical process of energization during the testing and commissioning of the electrical grid. The key step here is to execute energization strictly under the approved CSD procedure, ensuring we confirm phasing accuracy, in-service voltage and current correctness, protection stability, relay directionality, and overall operational readiness. We rely on reference documents and test boundaries, such as approved switching programs, energization permits, and protection setting packages to guide our work. Essential instruments include phasing sticks, multimeters, power quality meters, relay and SCADA tools, all accompanied by approved test sheets to ensure traceability and accuracy. The step-by-step process begins by confirming important prerequisites like the energization permit, switching orders, and safety boundaries. We then perform phasing checks by selectively energizing voltage transformers one source at a time, recording voltage and current immediately after energization to verify CT and VT connections and polarity. Next, panel meter readings and SCADA displays are compared with measured values to confirm system integrity. We thoroughly test protection functions, including directional and distance relays, earth fault, transformer differentials, and systems like AVR, ABTS, and recluse functions. After sufficient load operation, further checks like back-to-back and parallel testing are conducted with careful defect recording before restoring normal monitored operation. Our acceptance criteria are clear. Phasing must be correct, voltage and current values and phase angles within acceptable limits, stable protection circuits, successful in-service relay checks, and no remaining abnormal alarms. The result package compiles all necessary approvals, measurements, records, and operational handover documentation. Finally, a crucial hold point is established. No load transfer, source paralleling, or handover occurs until all phasing, measurement, and protection stability checks are witnessed and accepted, ensuring safe and reliable grid energization.